Hi, good morning to everybody. So in the last class, we have seen the second set of 4 principles in the green chemistry. In today's class, we will see the last 4 principles in the green chemistry. To start with, let us start with catalysis. The catalytic reagents, they are superior to stoichiometric reagents and they are as selective as possible. Before going into the principles, we will see few things about what is meant by a catalyst, what are the types of catalysts, then we will get into the principle. What is a catalyst? A catalyst is a substance which can activate a reaction. That is, it speeds up a reaction without altering its physical and chemical properties before and after the completion of the reaction. So by activating, it speeds up the reaction, so the rate of the reaction increases. As a result, it can save enormous amount of energy. There are 2 types of catalysis. One is homogeneous catalysis, the other one is the heterogeneous catalysis. Homogeneous catalysis, it takes place in only one phase. Say, for example, hydrolysis of an ester. Ester, it is in a liquid phase. To that, we add water and the catalyst used is hydrochloric acid or sulfuric acid. So, in this catalytic reaction, sulfuric acid, water and the ester all are in the liquid state. So, it becomes a homogeneous phase. So, we call it as a homogeneous catalysis. In heterogeneous catalysis, the catalyst and the reactants, they will be having different phases. Say, if the catalyst is in solid phase, the reactants will be either in the liquid state or in the gaseous state. For example, the Haber's process, that is the synthesis of ammonia, that is the fixing of nitrogen from the atmosphere. Here, nitrogen, it reacts with hydrogen to form ammonia and the catalyst used is iron and molybdenum is used as a promoter. In this catalytic reaction, iron and molybdenum, they are in the solid state, whereas the reactants, nitrogen and hydrogen, they are in the gaseous state. So being in different states, we call it as heterogeneous catalysis. With respect to the mechanism of catalysis, broadly, there are 2 types of theories. One is intermediate compound theory and the other one is adsorption theory. In the intermediate compound theory, first the catalyst, it reacts with one of the reactants and it forms the intermediate. So in the second stage, the intermediate will react with the other reactant to form the product and the catalyst is regenerated. Here, the intermediate which is formed when the catalyst react with the first reactant will be much more reactive than the reactant. So, the reaction gets speeded up and the rate of the reaction increases. And not only that, finally, the catalyst gets regenerated. In the adsorption theory, the catalyst and the reactants, they will be in different phases. So, the catalyst will be in a solid phase, the reactants will be adsorbed on the surface of the catalyst. Thereby, they will be on adjacent sides. So, the reactants present in the adjacent sides will react together to form the product. Once the product is formed, it will be thrown out from the surface of the catalysts. So, these are all the 2 theories, the mechanisms which explains the catalysis. Now, let us differentiate between the heterogeneous and homogeneous catalytic reaction. In the case of heterogeneous catalysis, the things will be in different solid phases. So, they will be in different phases. Whereas in homogeneous catalysis, all are in the same phase. Apart from that, in heterogeneous catalysis, they can be readily separated, but whereas in homogeneous catalysis, it is difficult to separate the catalyst and the products. In homogeneous catalysis, they are readily regenerated and recycled. But whereas in the case of homogeneous catalysis, they are a bit expensive and difficult to separate. So in heterogeneous catalysis, the rate of the reaction is not that fast, but whereas in homogeneous catalysis, they take place with a very high rates. Then diffusion is limited in heterogeneous catalysis and no diffusion controlled process takes place in the homogeneous catalysis. Then sensitive to poisons. In heterogeneous catalysis, they are sensitive to poisons. But whereas in homogeneous catalysis, they are robust to poisons. Then lower selectivity is observed in heterogeneous catalysis, but in homogeneous catalysis, it is of high selectivity. Here in homogeneous catalysis, the catalyst, it is long service life, but the catalyst is of short service life in homogeneous catalysis. The heterogeneous catalysis is a high energy process, whereas the homogeneous catalysis is a short service life. And with respect to the mechanisms, poor mechanism understanding is there with respect to heterogeneous catalysis, whereas the mechanism is fully well understood in the case of homogeneous catalysis. So, in the heterogeneous and homogeneous catalysis, in both the cases, there are certain advantages and certain disadvantages. So, if we combine the advantages of both the catalysts and if we can able to fabricate a catalyst, then that is called a green catalyst. Now, what are all the favorable conditions? With respect to the heterogeneous catalysis, they can be readily separated. So, that can be taken from the heterogeneous catalysis. Then they can be easily regenerated and recycled, and the catalysts have long service life. So, these three things we can take from the heterogeneous catalysis, and on the other hand, in the homogeneous catalysis, they have very high reaction rates, they are robust to poisons, they are highly selective, and mild condition is sufficient to carry out a reaction. So, these are all the favorable conditions to make the catalytic reaction very pleasing. So, let us combine all these things, and if we can able to find some catalysts, they will be termed as green catalysts. Then let us see one more type of catalysis, which is called biocatalysis, where the biological molecules are used as catalysts. These catalysts, they may be enzymes or the whole cell microorganisms. Here we have lot of benefits. First one, the reactions will be very fast. That is due to the correct orientation of the enzymes towards the reactant molecules. Further, due to this correct orientations, the site of high stereospecificity may be obtained. So, the reactions can be highly stereospecific. Then, these catalysts, they are substrate specific. That means, even if 2-3 reactants are there, it can react, it can go only with the selected substrate, so that the product will be selective and the yield will be very high. Not only that, these catalysts are water soluble, so no solvent medium is required. Water being a universal solvent, it is called as a green solvent, so it serves the purpose of the green chemistry. Then these catalysts, being living organisms, they are naturally occurring. So we can obtain them from renewable feedstocks, which is welcomed by one more, that is one another principle what we have seen in the last class. Then all the reactions which are taking place catalyzed by this biocatalyst, they need only moderate conditions. So there is a possibility for tandem one-pot reactions. To say an example for biocatalysis, fermentation of sugar to form alcohol. In the first stage, sugar it is acted upon by the enzyme invertase, which converts the sugar into glucose and fructose. In the second stage, this glucose and fructose is acted upon by an enzyme which is called zymase, which converts these monosaccharides into ethanol. Here, there is no question of side products. So the yield is very high, so it is eco-friendly. So that's the advantage of using the biocatalysts. Having seen all these types of catalysis and different types of catalysts, what is the net advantage of using these catalytic reagents? One, that is, the reaction will be having 100% atom economy. First of all, the catalyst can be regenerated. As a result, recovery becomes easier. Secondly, the yield of the product will be very high, and apart from the specific product, there is no chance for the side products. So naturally, the atom economy will be more. Secondly, the catalyzed reactions are faster. So if a reaction takes place faster, the rate of the reaction will be very high. It gets completed within a very short span of time, so the energy can be saved in this particular aspect. Of course, the reaction yields will be better, and not only that, selective reaction products. Suppose in a particular reaction, 2-3 products are possible. Maybe one may be a side product, or they may be isomers. We may need one particular isomer. So that and all can be obtained by using a catalyst. So maximum utilization of raw materials and minimum production of waste material takes place if we use the catalytic reagents. So put together, we can say it can save energy and reduce the burden of the byproducts. While selecting catalysts, the catalyst should be green catalyst. So we shouldn't encourage of taking catalysts in the stoichiometric ratio. Say for example, in Friedel-Crafts reaction, we are using aluminum chloride as the catalyst. So in this case, almost a stoichiometric quantity of the catalyst is required. After the completion of the reaction, the catalyst gets converted into aluminum hydroxide and it becomes a waste product. Getting rid of this waste product becomes one more problem. So we shouldn't take this type of catalyst, but we should see to that we are selecting only the green catalysts. Let us see few examples wherein we are selecting green catalysts. Say for example, the hydrogenation of propene, that is, hydrogen is added across carbon-carbon double bonds. So propene being the reactant, it reacts with hydrogen to form propane, which is an alkane. So here nickel is used as a catalyst. As yet another example, that is hydrogenation of methyl acetylene. Here methyl acetylene, it is having a carbon-carbon triple bond, and hydrogen has to be added across the carbon-carbon triple bond. Here the problem is we have to stop in the monohydrogenation stage. The catalyst used in this process is barium sulfate, which supports the palladium as the catalyst. So here only the mono addition takes place, and as a result the product is propylene. Another example is the same methyl acetylene, it reacts with methanol in presence of carbon monoxide. The same palladium is used as a catalyst to form methyl methacrylate as the product. So in these three cases, all the catalysts are green catalysts. So if we use catalysis, so it serves the purpose of the green chemistry. Now let us talk about the 10th principle of green chemistry, which is design for degradation. In the sense, chemical products should be designed so that at the end of their function, they do not persist in the environment and instead they break down into innocuous degradation products. That is, once the product is made, then after its function, it should totally degrade. It should not persist in the environment. But in few cases, the products, they have a permanent persistence. Say, for example, the sulfonated detergents. So, sulfonated detergents, they are sulfonates of long chain fatty acids. So, alkyl benzene sulfonates, so they persist. So, it has been largely noticed during 1950s and 60s. Then the formation of foam in sewage plants, then that is in the streams. The foams are due to the long chain alkyl substances. So, to avoid this, instead of having a long chain methylene groups, in between if we have a carbon-carbon double bond, then the product, it can be easily degraded and we can get rid of the persistence in the nature. Then one more compound, that is DDT, which bioaccumulates and causes thinning of eggshells. This DDT, it's a very good pesticide, but the problem is that is it is not degraded. Even in polar bears, the DDT is detected. Then yet one more example, we can take chlorofluorohydrocarbons. These chlorofluorohydrocarbons, what we are using in coolers and refrigerators, they enter into the atmosphere. So it takes a very long time to reach the ozone layer, and only in the ozone layer it reacts with the ozone layer, and as a result it will form a ozone hole which is harmful to the humankind. That is, the UV rays can easily pass through this ozone hole. So these are all the problems when the product, if they do not degrade and they remain in the environment permanently. So we should see to that whatever product we make, so it should be designed in such a way that after its function it should get degraded. And some advantages, it can be made to degrade using the sunlight, that is photocatalytically they may be degraded, and we should be careful in the degradation that the products of the degradation should not be harmful to the environment. So as far as possible, if we take the materials from renewable resources, say for example, if we take corn or wheat, the agricultural wastes as a feedstock, and if we take the substances from them and prepare polymers and other useful articles, they will degrade very easily. And not only that, they use 20 to 50% fewer fossil fuels when compared to the conventional plastics. And with this, the polylactic acid products, they are recyclable and they undergo degradation very easily, and it becomes a beautiful example to explain this principle. Then finally, the 11th principle, that is real-time analysis for pollution prevention. Analytical methods need to be further developed to allow for real-time in-process monitoring and control prior to the formation of hazardous substances. It means, as a chemist, in the real-time analysis, you should use it to check the progress of a chemical reaction. If it checks the progress of a chemical reaction, then he can stop the reaction at the right time so that he can avoid using excess energy. So this way, in each and every process, there should be an in-process control. So the in-process control in the sense, so they can monitor the temperature, the pressure, and suppose if it is a multi-stage reaction, each and every stage, so he has to monitor and he should see to that after the first stage a product has been formed, the right product has been formed, and it can be tested within a short span of time, and it should give clearance for the next reaction. Once the next reaction takes place, you should monitor all the conditions with respect to temperature, pressure, the concentration, so that the reaction takes place smoother. So if he follows the reaction, then no chance for the preparation of side products or the waste materials. So he can see to that he is getting a right product. So analytical methods has to be developed. So this is like this. Suppose if we drive a car, in the car there is no windows and rear mirrors. How to drive the car in a highway? Naturally it will end up in accidents. Suppose if the driver is provided with enough windows and a rear mirror, then he can comfortably drive the car and he can avoid the accidents. Like that, if enough real-time analysis, that is the analytical procedures, are given to a person who is working in a production area, then he can use all those things and he can get the right product using the optimum quantity of energy and avoid the waste materials. So that is what this principle insists. So we are towards the end of these 212 principles, and the last principle is inherently safer chemistry for accident prevention. So substances and the form of substances used in a chemical process should be chosen so as to minimize the potential for chemical accidents, including releases, explosion. Say that is the tragedy in Bhopal. It took place in India in 1984. See what happened, a poisonous gas, it gets emitted from a plant which kills 3,000 to 8,000 people in the spot itself, and subsequently due to radiation exposure some 20,000 people died and almost 1,00,000 people they suffered with lot of diseases in that area. Not only that, the land, the agricultural land there, we couldn't use it for agriculture. What happened? That is, methyl isocyanate was stored in drums in a particular place. So safety measures have not been taken. So suddenly water entered, it reacted with the methyl isocyanate, which results in the increase of temperature, so it explodes and emanates poisonous gas. Then the people naturally who are living in and around, who are working in that particular place, got affected, and it becomes a severe tragedy. So we have come to the end of this class. Hope you understood the last 4 principles of the green chemistry, that is catalysis, designing safer products, using real-time analysis, that is development of analytical procedures for in-process control, and development of safe technologies. So by this all the 12 principles are over. From the next class we will see in detail about the atom economy. Thank you.